This recording is for the Unit 5 labs. So question 1, of course, is that you, the student, will attend the lab intensive. Question 2, look at Lab 5, stress and strain objectives. You will find Young's modulus and the elastic behavior and fracture point of a rubber band are the only two objectives. In the theory part, you will see this statement. Rubber is a non-Hookean material because its elasticity depends on the stress. Steel, by the way, it doesn't. It's a Hookean material. And then this statement. Okay, this question here. How often, and here for stress and strain, again, you have to look at the procedures in the lab manual. How often do you measure the original length, width, and thickness of the rubber band using which unit? You measure each of them just once in millimeters. Which are the only two variables measured throughout the experiment? Using which units? Length and mass, millimeters, and grams, and so on. They should be in the correct order, and again, I want you to read through the lab manual. Same lab, stress and strain. The example, you will find these. And notice that apparently in the lab manual I have one set of numbers in blue, while in the video I actually used different kind of numbers, but both apply, both of them are the examples. In the procedure, in the example here, the Excel graphs the data right away. And once more data are entered, click on the computed value and so on. You can read through these statements. Question 6 now is about the lab on hydrostatic pressure. These are the objectives. There are 3 of them, these. Then this is the theory part. Again, they're in the correct order. When a container has a hole orifice drilled into it and is then filled with fluid, that fluid experiences the hydrostatic pressure. Pressure equals density of the water times gravity times height, with h being the water depth or height above the orifice. Bernoulli's equation, when you look in the theory part, yields Torricelli's law. Neglecting air resistance, the fluid's trajectory is described by the kinematic equations, and so on. So these statements here are mostly in the correct order. Which parameter is fixed throughout the experiment? The vertical distance y, which feeds into the kinematic equations, which are 2 variables measured throughout the experiment. The horizontal distance x, also for the kinematic equations, and the depth h for hydrostatic pressure. Should the meter stick be flush with the hole in the bottle, and so on? 3 questions here, and you will see yes, yes, yes. Since you measure everything in centimeters, which value should you use for g, the acceleration due to gravity? If you do the lap in Alaska, 982 centimeters per second squared. If you did the lap in the lower 48, you should use this value. Our lap intensive is going to be in Alaska, and we'll be measuring in centimeters, so at 982. Notice that this statement here, which I didn't check, would be also correct values. However, we're more likely to measure the short distances in the lab in centimeters than we are in meters, so we'll be using 982 centimeters per second squared. That's why you have a gap here in the answers. Jumps from D to F. So this one here is, for which part of the water stream should you measure the horizontal distance? Explain. You should measure to the furthest part of the water stream, because any water short of that has already lost kinetic energy due to the water's viscosity. Why is time not measured? Because so it turns out in the algebra that we actually don't need it, and we get all the information from what we will measure, which is the height, the depth of the water column, and the distance that the water runs out. How should the 2 computed velocities, hydrostatic and kinematic, compare? The water should spout with a velocity Vp, and it does spout with a velocity Vx, and those should equal each other unless there's a hidden surprise. Why may they not be the same? And here's the answer. And this last one here then, if you have to screw the lid back on the bottle, the water will stop running after a few seconds. Explain, and here the correct answer. Don't use the word vacuum, because this is the correct answer here. There still is air in there, it just expands more in, so the pressure is lower. And I don't give too much away if I check these here as well. The example for that, you will find these three in the example and lab manual. The other remaining two statements might be still correct, it's just you're not going to find the lab manual. And the idea, of course, is that you look at the lab manual and complete the pre-lab from there. All right, that's the recording for Lab 5 pre-labs.